that ends chapter 1, which went by faster than I thought. So we'll get into chapter 2, section 1, organizing qualitative data. Objectives: organize qualitative data in tables, construct bar graphs and pie charts. Quantitative data, that's the easier thing, but what do you do with qualitative data? Thinking back to yesterday, qualitative data, things that can be categorized but not necessarily ranked. An easy one would be something like eye color or hair color. Car manufacturers, things that cannot be necessarily numerically assigned. Organize qualitative data in tables. When data is collected from a survey or designed experiment, they must be organized into a manageable form. Raw data, this is the data that is not organized. Ways to organize data are to put them in tables or graphs or numerical summaries. So we'll cover that in chapter 3. Frequency distribution. A list of categories of data, the number of occurrences for each category of data. You have your list of data, you have the known outcomes of it, then you just say, okay, this was category A, okay, check. Category B, click. Category C, click. And you just keep on doing that until you've gone all through the data. Then once you've tallied everything, now you can tabulate the final score for each of the data. Example number 1, a physical therapist wants to determine the types of rehabilitation required for her patients. She obtains a simple random sample of 30 of her patients and records the body part requiring rehabilitation. Construct a frequency distribution of location of injury. Raw data will look something like this. It's not ordered in any particular way, it's just there. But notice that you don't have 30 different classifications, you really only have a few classifications. Notice it's just hand. I don't know if it's the right hand, left hand. It's just the hand. Is it the palm of the hand? Is it the fingers attached to the hand? I don't know. The back, okay? Is it the lower back, the mid back, upper back? I have no idea. It's just the back, the shoulder, the knee, the neck, wrist. So some of these are fairly small. It's fairly easy to understand what's being looked at. The back is fairly broad, mid back, lower back, upper back could have an influence. This would be the raw data. Now you tally it. The first column of your table lists all the classifications that there are, and then you just go through them all and tally them. Once you've tallied them all, you've gone through all 30, then you say, okay, the back is now 12, wrist 2, elbow 1, hip 2, etc. The only thing that's of interest is the first column and the third column. The tally is not relevant. Also, note that the frequency adds up to 30. If you add up all of these things, it should be the original number that you started with. That's a check that you can do when you're doing something like this. Relative frequency. This is the proportion or percentage of observations within a category and is found using the formula frequency of item divided by the sum of all frequencies. You can have a relative frequency distribution with this. A list of all categories of data with the relative frequency for each category. Example number 2, use the frequency distribution obtained in the prior example one to construct a relative frequency distribution. Remember what I said? If we're dealing with just the frequency distribution, then columns 1 and 2 are the only thing of interest. Now, since we're asked to do a relative frequency, now we're going to add a third column. The total was 30 for the frequency. We're going to take that 12, and the relative frequency would be 12 over 30, which is 0.4. Now, in this case, it's exactly 0.4, but in the next row, 2 over 30 is roughly the squiggly equals. All that means is roughly is 0.0667. The elbow, 1 over 30, 0.0333. The shoulder, 4 over 30, 0.1333, etc. Note that each decimal was rounded off to the 4th decimal place. This you need to decide before you display the relative frequency. Bar graph. You might know what a bar graph is. Bar graph is constructed by labeling each category of data on either the horizontal or vertical axis and the frequency or relative frequency of the category on the other axis. Rectangles of equal width are drawn for each category. The height of each rectangle represents the category's frequency or relative frequency. Example number 3, use the data summarized in the previous table in examples 1 and 2 to construct the following: a frequency bar graph and a relative frequency bar graph. Remember, this was our frequency table. You can pretty much ignore this part here. And there's the bar graph. Notice for the horizontal axis, all you have are different categories for each of the possible body part: back, wrist, elbow, hip, shoulder, etc. For the vertical axis, you're going to pick out the maximum value that occurs, and that will determine how high this frequency axis will go. Since the maximum was the first one, that is back, so 12, this vertical will only go up to 12. Now, notice that there's a little bit of space above the bar graph. How much space you have above it, that's up to you. Sometimes researchers may tack on one additional on top just to give space. Whatever the case, the elbow was 1, so that's going to be halfway between 0 and 2. The knee was 5, so that'll be halfway between 4 and 6. You could do the same thing with a relative frequency table. Oh, Mr. Norman, it looks like the same thing. Yes. Outwardly, whether you're using relative frequency or just plain frequency, the bar graph for each should look the same. The only difference is the y-axis, the vertical axis. Notice over here, for the vertical axis, that represents the frequency, and it went from 0 to 12. The relative frequency, it's not going up to 12, it's only going from 0 to 0.4. Remember, the back had the highest relative frequency at 0.4. The black bar graph goes up to 0.4. Now, for example, 0.1, 0.2, 0.3, 0.4. Now, suppose your ticks are represented in this fashion in jumps of 0.1, 0 to 0.1 to 0.2, 0.2 to 0.3, etc. But suppose your back went high as 0.45. If you have a good graph, you won't say Oh, 0.45 here. No. What you do is you'll just go up to the next jump because your jumps are consistent 0.1, 0.2, 0.3, 0.4, and zero point 0.5. This top one is going to be bigger than or equal to your highest, your largest relative frequency. This 0.45 is going to be in between the 0.4 and 0.5. Pareto chart. A Pareto chart is a bar graph where the bars are drawn in decreasing order of frequency or relative frequency. It's the same as a bar graph, but is a special bar graph in that there's some order to this and that the order is in decreasing fashion. Here's the relative frequency, ordinary relative frequency bar graph. Here's the same thing in form of a Pareto chart. The highest is the back. The next highest is the knee. The next highest is the shoulder. You actually have a three-way tie between wrist, hip, and hand. Now, in this case, where you have a two or more way tie, how are you going to handle the classifications? Are you going to put them in alphabetical order or in the order of how they appeared in the list of categories? That's up to you. Many times people will just put it in alphabetical order, hand first, then hip, then wrist. It's just a reordering of the bar graph so that the highest is on the left and the lowest is on the right. Side by side bar graphs. Suppose we want to know whether more people are finishing college today than in 1990. We could draw a side by side bar graph to compare the data for two different years. Data sets should be compared by using relative frequencies. If you're doing the side by side bar graphs, this is the important part here. You're going to use relative frequencies because different sample or proportion sizes make comparison using frequencies very difficult or misleading. For example, what proportion of people got cars between 1940 and 1980? The problem is between 1940 and 1980, the population of the US doubled. You can't use frequencies because you might get the impression everyone in the country is getting a car. No, it's just that the portion of the people who have cars in 1980 just happened to match the population of the US from 1940. I'm just making that up. I really don't know if that's the case. I'm just pointing out if you're doing these side by side bar graphs, you need to limit yourselves to relative frequencies. Comparing two sets of data, the following data represent the educational attainment in 1990 and 2017 of adults 25 years and older who are residents in the United States. These data are in thousands. So 39,344 truly represents 39,344,000. Draw a side-by-side relative frequency bar graph of the data. Note the characteristics of the population being studied are adults who are 25 years or older and who are residents of the United States. Here's the frequency table. Education attained, not a high school graduate, high school diploma, some college but no degree, associate's degree, bachelor's degree, graduate or professional degree. For 1990, you have these frequencies. And instead of writing out 39 million, we shorten it by saying these represents thousands. 4 would represent 4,000. 105 would represent 5,000. 137 would represent 137,000. It's just a condensed way of representing numbers here. You notice that in 1990, the total was 100, just under 160,000. And 2017, it was just over 220,000. This is how it looks like. Notice the vertical, you have relative frequency. Relative frequency is far easier to compare. It takes less headspace to try to compare relative frequency or percentages, if you will. Notice on the upper right corner, you have a key to tell you what color represents what year. And notice that for each category, the bars are side by side. If you look at this table, you can actually notice a pattern. Don't look at the heights of the bars, but look at the difference in the heights. Notice that you have a big difference here in favor of not a high school graduate. So when you get to the next category, that difference in favor of 1990, not a high school graduate, big difference in favor of 1990. For high school diploma, there's still a difference in favor of 1990, but it's much smaller. Now, when we get to some college, but no degree, there's a small difference, but now it's in favor of 2017. And now that gap is widening and widening even further. And it peters out right at bachelor's degree. So graduate or professional degree. You can, just by looking at this, you can distinguish a certain pattern. The higher level of education you go, the difference starts off favoring 1990, but the higher you go, the differences starts to favor 2017. Oh, key note, the side-by-side bar graphs only properly work or make sense when you use relative frequencies. Horizontal bars. Bar graphs may also be drawn with horizontal bars as to vertical bars in the previous cases. Horizontal bars tend to be preferable when category names are linked, such as this. The same graph as before, but because the names, the categories tend to be long, it's horizontal. Now it gives you breathing space to write out all of these long categories. Oh, interesting. This is not the same thing. The first one was 1990 versus 2017. This one is versus 2013. Huge difference, marginal difference with the high school diploma, some college degree, big difference favoring 1990. The first three all favor 1990. There is a pattern, but it's not the same one in 2017. Something to look at. Constructing pie charts. A pie chart is a circular divided into sectors like pie slices. Each sector represents a category of data. The area of each sector is proportional to the relative frequency of the category. Note that within each category, the area of each sector is proportional to its relative frequency. Again, you're not going to be using frequency in this case. You're going to be looking at relative frequency. The following data represents educational attainment of residents in the United States 25 years and older in 2017, based on data obtained from the U.S. Census Bureau. The data are in thousands. Construct a pie chart of the data. Here's the data. You have the frequency, the relative frequency. You can convert that to degree of measure for each sector. Note the sum of the frequencies 221,151 And for each category, frequency over n times 360, this gives you the degree of measure. If you multiply the 0.2101 by 360, you should get roughly 43 degrees rounded off. 360 times 0.2713, again, 98 plus change, but you round it off, it becomes 98, et cetera, et cetera. And you get something like this. Notice the how each sector is labeled. If you have space, then you can write the category and its percentage within that space. If you don't have the space, you can write it outside and then point it to the sector that represents it. Okay,